Hey guys, Miss Marusic here, and in this video we're going to be talking about molarity calculations of solutions. Molarity itself is defined as the number of moles of solute per liter of solution, and that is the way that it's shown on our formula chart in the gases, liquids, and solutions section. You'll notice molarity, big M, moles of solute per liter of solution. Now we do have to be very careful with that big M. There's another place where we had big M, which is the equation up here that the number of moles equals mass over molar mass. This big M is bolded, so when the big M is bolded, it is for molar mass. However, here the big M was not bolded, and so that would be for molarity. So make sure you notice and can distinguish the difference between those two. However, what's interesting is that this moles equals mass over molar mass, I could use as a substitution in for moles here within molarity. So to see that in action, first off, what if I took this statement here and rewrote it as a more standard formula setup? I might write something that looks like this. Molarity equals the number of moles of solute over liter of solution. However, we want to keep in mind that a lot of times problems don't give us moles off the bat. They might give us a mass, a number of grams. And so you kind of have some options there. You could take your grams and convert it into moles using stoichiometry, would be a one-step quick calculation. Or you could make in the substitution the number of moles equals mass over molar mass, and then you would be able to solve your problem. So keep in mind that you could use that as a substitution in, but we got to make sure we recognize the difference between those two big M's there. Now, as far as the units for molarity, you could either report moles per liter or big M. They mean exactly the same thing. If you had a free response question, AP would not care which of those two units you used. However, you do want to be familiar with both because I've seen problems where they've used one or the other, and so you would need to know that they mean exactly the same thing. Now, if they give us a molarity, we could use that molarity as a conversion factor. For example, let's say they told us that our molarity was a 2.0 molarity solution. What that would mean is that I had 2.0 moles for every 1 liter of solution, which would be very helpful if I was trying to say do a stoichiometry problem. So we'll see how to utilize that in our next video. Some other ways to communicate this would be, hey, if I had 2.0 moles dissolved in enough water to make 1 liter of solution, I could report it as 2.0 big M, 2.0 moles per liter, or we could even say that we have a 2.0 molar solution. All of those statements mean exactly the same thing, so keep in mind that they can be used interchangeably. Now, it says here that molarity is the most common way of expressing concentration of solutions. There's all kinds of other concentration units out there. There's parts per million, parts per thousand. You could do a percent by mass. You could even use something called molality, which uses a kilograms instead of a liter situation. But if you were to go into a chemical storeroom and look at the solution bottles in that chemical storeroom, you would notice that all of them have their concentration reported in molarity. It is by far the most common unit that is used. So keep that in mind that there are other units out there, but molarity is kind of the major one that is utilized. An increase in molarity would mean that the solution has become more concentrated. Now on this next one here, it says a decrease in molarity means that the solution has become, and you might have been tempted there to put less concentrated. Well, it is less concentrated, but we can also say that that solution has become more diluted at that point. So being concentrated versus being a diluted solution are exactly the opposite thing. Now, let's say I was trying to actually make a solution of a particular molarity. There's a very set piece of equipment I would need to use, and that is what is called a volumetric flask. A volumetric flask is a piece of glassware that has an etching on it that tells us when we've reached whatever volume is reported on that specific piece of glassware. So you notice down here there's some various sizes of volumetric flasks. In our chemical storeroom, I think we have anywhere from as small as 10 milliliters all the way up to 2,000 milliliters. So we have a wide ranges of sizes. But even with that wide ranges of sizes, there might only be one of those that's appropriate to use for our specific experiment, depending on how much solution we're trying to make. So even though there's only one marking on that piece of glassware, it is very precise for that one marking. Volumetric flasks are really only used to make solutions. It's really kind of their only purpose, but they're very good at making those solutions. So basically how the process would work is that you would first need to perform some sort of calculation where you figured out how many grams you need of your particular solute in order to achieve the particular number of moles of solute that you're trying to measure. So then you would mass out that many grams on a balance, and then you would want to add that mass to a volumetric flask that already had a little bit of water in it, so that way it could go ahead and start that dissolving process. Now, when you're adding this, if you're only adding in a little bit of solid, you might be able to do it with just a funnel and kind of pouring it in and rinsing off that whey boat as you are dispensing that solid into your flask. However, if you have a lot of solid that you're trying to put in to where you're worried it might clog up the funnel, you could dissolve a little bit of this into some dissolved water first before you pour it into your solution. You wouldn't want to use too much water when you're doing that. You wouldn't want to, dissolve it too much, but enough that then you could get it into here to finish mixing up your solution. So then what you would want to do is you would want to stir and mix that up. This is using what's called a stirring plate. It has a magnet that ends up spinning in order to dissolve that solution. And then once you feel like it's been well dissolved, you would continue to add water until it reached the etching, the lined mark on that neck of the volumetric flask. That tells you when you've reached that particular volume. Now, one of the other things then you would want to do, even though this picture doesn't show it, is you would want to stopper that and turn it over a couple times to make sure that that entire solution has been well dissolved. To see this process in action, I would encourage you to watch this video clip down here. This actually shows a real-life preparation of a solution, and it's definitely different to see in person than me just explaining it to you. So again, I would encourage you to watch that particular video clip there. All right, let's go ahead and see how we would perform some of these calculations here. So it says to calculate the molarity of a solution prepared by dissolving 4 grams of solid sodium hydroxide in enough water to make 200 milliliters of solution. So the first thing I would want to do here is I would want to kind of figure out what formula I might need. What kind of pieces of information do I have? I see that I'm trying to calculate the molarity. I see that they've given me here a mass, and I see that they've given me a volume here. And so once I see that I have a molarity calculation on my hands where they've given me mass and volume, first off, I know I would want to use molarity equals the number of moles over a liter of solution, and a lot of times I'll just write the unit moles over liter to remind me what needs to go where. However, I notice that I don't have moles quite yet. Right now I have grams, so either I could do a grams to mole conversion for that, or here in for moles I can make in the substitution of mass over molar mass. And I am going to go ahead and write out molar mass here versus using the bolded M, so that way I remember which M is which here, because I know those can get kind of confusing. All right, so now that I kind of see what pieces I need, I already have my mass. I already have my volume, although it is not in the right unit, so we will have to address that here in a moment. But I do need my molar mass of sodium hydroxide. Now, sodium is +1. Hydroxide is -1, so those cancel each other out. And so I'm going to go find my molar mass of NaOH. Sodium is 22.99. Hydrogen is right about 1.01. And then oxygen, as we know, is 16. Interestingly enough, this one comes out on the nose to be 40 grams per mole. That doesn't come out that often to be on the nose a particular value, but this one sure does. All right, so now I'm going to go and plug everything into my equation here. My molarity is going to be equal to my mass of 4 grams over my molar mass, which was 40 grams per mole, divided by my liters of solution. Now, remember, milli is 1 times 10 to the negative third, so I'm going to need to move that decimal over 3 places. And so 200 milliliters would become 0.200 liters. All right, so now I'm just going to plug in all of that data into my calculator. So I'm going to have 4 grams divided by 40 grams per mole divided by 0.2 liters, and that gets me a value of 0.5. Now I do want to address sig figs here for just a minute. If I look back at my original data, I noticed that both of these numbers had 3 sig figs, so I'm going to give this 3 sig figs as well. Now as far as the unit, grams canceled, so that left me with moles over liter, and I could leave the unit like that, or I could report 0.5 molarity. Either of those units is appropriate. Now, as far as preparing the solution is concerned, the first thing I would want to do is to mass out that 4.0 grams of NaOH, since I already did my calculation, and I'm going to do that on a balance. Remember, we do masses on balances. All right, so then I'm going to put that NaOH into a very specific size volumetric flask. Here, this calculation was specific for 200 milliliters. So I can only use a 200 milliliter volumetric flask. If I had a bigger volumetric flask, then I would need a bigger amount of grams in order to accommodate for that same molarity, that same concentration. So I am going to use a 200 milliliter volumetric flask. With some water. So then, last but not least, I add water to the line, and what I mean is that etched line that's on the neck of the flask, and then we mix. Now, I know this is kind of a simplified version of that process, but at least gets the point across that you knew that you had to mass out your substance, that you had to put it in a very specific size volumetric flask, and that you would want to add water and mix. So it gets those basic points across. All right, let's go ahead and do another calculation here. On this one, it says, hey, I have 1.56 grams of gaseous HCl, so that's going to be a mass. Then I have 1.60 molar HCl solution, so they actually gave me a molarity here. And it wants to know how many milliliters of solution were made, and so that's going to be a volume that I'm looking for. However, I have to be aware that it wants this volume in milliliters, and as we know, our calculation usually comes out in liters, so we will have to do some sort of conversion at some point. So I am going to use my molarity equals moles over liter formula. However, I'm like, I have mass again, so you could either do a mass to moles conversion off the bat, or as we did earlier, you could substitute in here mass over molar mass into this calculation, which is the way I'm going to do this. So I do need to quickly find my molar mass of HCl. And so to do that, I would again look at my periodic table. Again, hydrogen, just like earlier, is right around 1.01. Our chlorine over here would be 35.45. And so that gets me a molar mass value of 36.46 grams per mole. And so I'm going to plug all of those pieces in now into my formula. So I'm going to have my molarity of 1.60 big M, which equals my mass of 1.56 grams over my molar mass of 36.46 grams per mole over my volume, which I'm going to go ahead and put X here to calculate. Now, I have a problem. My X, my unknown variable, is in the denominator. So one of the very first things I would want to do is get that out of the denominator. That's a really bad place for it. And so to bring it up to the top, I'm going to multiply this other side by X. So multiplying both sides by X would cancel it out on this original side over here. So now to get X by itself, I would want to divide both sides by the 1.60 molarity. So, to plug into my calculator here, I would have 1.56 divided by 36.46 divided by 1.60. And that gets me this lovely value right here. And I'm going to go ahead and use 3 significant figures since all my original numbers had 3 sig figs. And that's 0.267. Now, let's talk unit for a minute. This one is not as obvious to see the unit off the bat because of the way that this was in terms of molarity. But if you remember here, molarity is the same thing as writing moles over liters. So if I kind of look here, what's all canceling, grams and grams cancels, moles and moles cancels. So that leaves me with a divided by liters. The 2 divided bys cancel each other out. And so this comes out in liters. However, we got to be careful because this problem wasn't asking for liters, but rather for milliliters. So I would need to convert it back. Oops, I forgot a 0, didn't I? So let me go back to my calculator here. That had that extra 0 in there, so that was my bad. I wrote that incorrectly. So now when I move my decimal over 3 places, I would come out to 26.7 milliliters. So apologies for my error there. This would be your final number here. All right, let's look at another type of calculation I could do, and that is what is called a dilution. A dilution is the process of making a solution less concentrated. If you've ever had a really concentrated drink mix before and you've wanted to dilute it down to where you can actually drink it, think about how you would do that. This is usually done by adding more solvent, typically water, to that solution. And as I do that, what happens is that something that started off with a really high concentration, that had a very high molarity, but a low volume, as I add that water in, or whatever solvent I have, the molarity would decrease. It would become less concentrated, but the volume overall would increase to it. So when we add more solvent, we lower the concentration, which makes the solution more diluted. Now, there is a formula that we can use to perform dilution calculations. However, we need to be really careful that we're only using it in a dilution situation. And that is this formula right here, that V1M1 equals V2M2. Sometimes referred to as the VOOM formula for solutions, because if you read it all in a row, it looks like you say VOOM. So how this works is that basically you would have your initial volume and initial molarity value, and then depending on how much you added volume-wise of solvent to your solution, you would have your new total volume here, and then your new molarity here. So we do have to keep in mind that this V2 is the total new volume, not how much you added to the solution. So you've got to be careful when working with that particular one. Now, for the volumes, they can be in any unit here. It doesn't matter as long as they're in the same unit. So let's kind of look and see how this would work in a calculation. So this problem asks what volume of 16 molar sulfuric acid would be needed to make 1 liter of a 0.1 molar solution, and how much water was added to achieve the dilution. So I'm going to go through and kind of identify variable-wise what I have happening here. I notice it's asking for a volume, giving me this here as a molarity, and then I have a new volume and a new molarity that I achieved after I diluted it down. It also asks how much water was added to achieve the dilution, and anytime I see the word dilution there, I see 2 volumes and 2 molarities. That's a key to me that I'm using my V1M1 equals V2M2 calculation. So what I would want to do is kind of identify which of these situations is my initial and which ones are my final. Now, it really doesn't matter what you put as the 1s and the 2s as long as you pair correct things together. So really, this volume and this molarity need to go together. So I'm going to call those the 1s, and I'm going to call these guys the 2s since they went together as well. Now, this is a really common calculation and process that we have to do when preparing solutions in lab. We order very concentrated stock solutions of many of our acids. And so before we use them in laboratory, we have to dilute them down with water to prepare them for use in whatever lab we're dealing with. And so depending on the lab, I might need a certain amount and a certain concentration of that acid. And so this is a very common calculation that I have to do when I'm preparing solutions to get ready for lab. So to kind of see how this calculation would work, I'm going to just plug everything in here. I'm looking for V1, so you can either write V1 or you can write X there. My M1 would be 16 molar. My V2 would be 1 liter. And my M2 would be 0.1 molarity. So again, I had a really concentrated solution that I'm diluting down to make this much weaker concentration and this new total volume. So this volume is going to be much smaller than this 1 liter because I'm diluting it to get to this 1 liter. So next thing I would want to do is plug in this calculation into my calculator. To get V1 by itself, I would want to divide 16 over. And so that's going to give me 1 times 0.1 divided by 16. Now this number does come out really small, and I'm going to try not to forget a 0 this time. This gets a V1 of 0.00625. And unit-wise, since the other volume was in liters, this would come out to be liters as well. Now, let's be real here. That's not the most helpful unit to use when I'm trying to measure out. Most of our graduated cylinders and burettes that I might use to measure this out would be in milliliters. So I'm actually going to convert this. I'm going to move my decimal over 3 places to get into milli. And so that would give me a value of 6.25 milliliters. So in thinking about the preparation process here, what that would mean is that I would want to measure out 6.25 milliliters of 16.0 molar H2SO4. And what I would do is then add that to a 1 liter volumetric flask, and then I could fill that up the rest of the way to the 1 liter and have my total solution. So I could very easily use a volumetric flask to prepare this. However, I technically don't need a volumetric flask to do this one. I do for the solids, but for this one, since everything is in terms of volumes, I could measure out the volume of everything I needed. To get the other volume that I need of the water, I need to think about how much volume would I add to 6.25 milliliters in order to get to this new total of 1 liter. Now, 1 liter is the same as 1,000 milliliters. So if I take that 1,000 milliliters and subtract off the 6.25 that I know are going to be that sulfuric acid, then that difference of 993.75 milliliters will be water added to that sulfuric acid. So in order to dilute that very concentrated sulfuric acid down, I'm going to add a ton of water in there until the 2 volumes would add up to my new total volume of 1 liter or 1,000 milliliters. All right, hopefully we're feeling good about molarity calculations and preparation of solutions. We're going to be in the next video doing a few more calculations with molarity just to make sure we feel good about all the different types of situations that we could use it in. If you have any questions or need any help, please feel free to email me. Bye, guys.